Okay, last class we stopped talking about, well, when we stopped, we had looked at this theorem that said that every bounded monotonic sequence converged. And I didn't have a chance to actually show you an example. I said I would come in today and I would actually do that. I kind of lied. All right. Because of the time it will take me to do that, and I really want to get into 8.2 to start, I did the homework problems from 8.1. There were problems numbers 37, 38, 39, and 40. Did I assign those last time? Yeah. I did, but I said we couldn't do them, right? Wait. So I did those in this video, and while I'm doing the video, I'm actually explaining how we use this theorem and the proper way to use this theorem for these problems, all right? I think it's a pretty decent video. It's probably about 20 or 30 minutes long. That's about how long it would have taken me to explain it. So that's your homework. Part of your homework is to just watch that, all right? That way we can get right into 8.2? All right. Got it, got it. We're recording and good. So 8.2. Series. All right, so we're going to start series. I'm serious about this. So what is a series? A series is a pretty simple definition, all right? Given a sequence, A sub n, so we know what a sequence is, right? Sequence is just a list of numbers, right? So given a sequence, A sub n, we add the numbers up. That's all we do. We add them up. So you take that list of numbers and you just add each of the numbers together. So it looks something like this. In the case that our sequence was finite, meaning we had a fixed number of numbers, it would look like a sub 1 plus a sub 2 plus a sub 3 until we get out to the very last one, which I'll call a sub n. All right, that would be a finite series. In the case that our series is infinite, our sequence is infinite, we get what's called an infinite series. And that would look like this. A1 plus A2 plus A3. And that would continue forever, wouldn't it? So if I take a number, in the case that we're in a finite series, if I take a number and add another number and add another number and add another number, and I keep doing that and I stop at some point, I should get an answer, shouldn't I? I should get a numerical answer, right? There should be no problems there. I mean, I'm like sitting there on my calculator, I'm adding, and then I stop, I should have a number. So when you look at a finite series, this sum should always become something, right? A number, nice and fixed number. Number, fixed, done. So we're not very interested in finite series. What we're more interested in is something like this. So if I take numbers and add them up together forever, which would be impossible for me to do, the question is, does this turn out to be a finite number? What do you think? Yes? Well, okay, let me give you an example. 1 plus 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 1. Would that turn out to be a number if I kept adding forever? It'd be infinite, wouldn't it? So it looks like possibly we could have infinity, right? But then we could add something like 0 plus 0 plus 0 plus 0. And that would add up to be a number, wouldn't it? 0. So there's a question in this. What happens to this? Does it add up to be a number or does it not? Does it get really big? Or does it do something weird like, what's 1 plus negative 1 plus 1 plus negative 1? Something like 1 plus negative 1 plus 1 plus negative 1 plus 1. You see what I'm saying here? What does that add up to be? 0? That's an interesting question. That's actually a very interesting question, but it's too early to answer that right now, okay? So you might say 1, right?
Depends on where it ends.
Yeah, see, but it doesn't end. That's the trouble, right? See, look, if I cover up this first one right there, then you could say that these two cancel, those two cancel, next two cancel, right? They all cancel, so your answer should be 1, maybe. And then if you say, no, don't cover up that one, then those first two should be 0, and then 0, and then 0. And so it should add up to be 0. So which one is it? Physicists would say 1/2. Okay, it's beyond what just the idea though. Look, we will address this, just not yet, okay? So the idea that we have here today is that we started with the sequence, a list of numbers. If we add up a finite number of them, there's not really any question. It's a number, right? If we add up an infinite number of them, we actually don't know what's going to happen necessarily. And that's what we're interested in. Does a series actually add up to be something or not? So let's get some notation out of the way. Notation. For an infinite series, we've seen this before? Yes? This is the sigma, right? This means summation. If you haven't seen it, it's okay. If I write n equals 1 to infinity, it tells you I'm going to start at n equals 1, and I'm going to stop, well, I'm never going to stop. I'm going to go all the way to infinity. And then inside here is what I want you to add up. And in this case, I want you to add up that sequence I called a sub n. So that notation right there means you start with 1, right? Replace this n with 1, which would be a sub 1. Then plus, because it's a sigma, the sigma means sum, plus, now you let n be 2. Then plus, now you let n be 3. And then n be 4, and n be 5, right? Plus dot, dot, dot. Does everyone see that this notation right here is just a condensed way of writing that out? Yes? It's a shorthand notation for writing out an infinite number of additions. Now, what if I don't want it to be infinite? What if I actually want you to stop somewhere? Well, I could do this. I could do like n equals 1, and I could stop at, let's say, instead of infinity, I could use any letter I want. How about capital M? And I still use a sub n here, because n is the thing that's going to change. And this would be a1 plus a2 plus dot, dot, dot until I get to where? A sub m. So this is a finite series. This is an infinite series, right? See the difference in notation? Any questions? The next thing is a definition. The definition here is what we call the nth partial sum. So given some infinite series, so I did something to you there. What did I do? I changed the letter, right? Instead of using n equals 1 to infinity, I used k equals 1 to infinity. Okay, and I'm free to do that. This is called a dummy variable. It's just my index. I can use any letter I want. We usually use n or k or j. That's usually what we use for indexes, but you could use anything you want there. Notice that this changed to k also, right? So this is exactly the same as this, right? It's going to create the same exact thing. A1, A2, A3, A4 added together. So if I'm given an infinite series, the nth partial sum means, well, exactly what it says. It's part of the total sum. It's not the whole sum, which is to infinity, right? It's part of it. What part of it? Well, the part till I get out to n. So this is the way we denote it. The nth partial sum, capital S sub n, is equal to sum k equals 1 to n of a sub k, which is a1 plus a2 stopping where? N, a sub n. So I should also point out the nth partial sum, we do these on infinite series. So if someone gives you an infinite series, we know that it would be impossible for us to actually physically go out there and add every number up, right, forever. So what we look at is what we call the nth partial sum. We actually add them up and we actually stop somewhere. We stop at n, and it's part of the sum. It's the nth partial. Make sense, the language? Okay. So given us an infinite series, that's what the nth partial sum is. Now, we move on to another definition. Given sum, I'll use k again, k equals 1 to infinity of a sub k. So that is what? We're given a what there? An infinite series. So if someone gives us an infinite series, then if the limit as n goes to infinity of s sub n equals, let me see what they use here, little s, then we say that the infinite series converges. Let me try and explain what we mean by this. What did it mean for a sequence to converge? A sequence. Those dots, right, were headed somewhere, right? Those dots were headed somewhere. This is saying that the infinite series will converge if the sum, right, if we stop somewhere and figure out that sum, and then let n go to infinity, that goes to a number. And this is a confusing concept for a lot of people, so let me try and illustrate this with a picture, all right? Let me also put here, otherwise we say it diverges. Otherwise, it diverges. Okay? So I'm going to give you an example that will hopefully illustrate this in action, okay? Here we go. So as an example, let's take at a sequence 1 over n. Let's look at, I'm asking you to investigate this summation. Now I'm going to be doing a lot of things here as I work through this. I'm going to be using different letters, and I want to make sure everyone's comfortable with it. So let me know if you're thrown off by any of the letters, all right? I defined here a sequence, didn't I? That's a sequence. This is an infinite series. It is based upon that sequence, isn't it? I want to know what's going on here. So first, let's look at the sequence itself. A sub n is the sequence of numbers 1, 1/2, 1/3, 1/4, 1/5. Keep going, right? Does this sequence converge? Yes, right? The sequence converges, and we could do that. That was your homework from last time. You just take the limit as n goes to infinity of this. That would go to 0. This sequence converges to 0, right? We know that much. But I want to talk about the series. The series looks like this. I'll just do it up here. It's 1 plus 1/2 plus 1/3 plus 1/4 forever, isn't it? Does that converge? No? You don't think so? Yes? The sequence converges, right? We have to understand the difference between the two. The sequence converges just means that each one is headed, as you go out further, each one of these is headed closer to a number. For a series to converge means that this sum taken forever goes to a number, which we call little s. Yes?
My guess would be 2.
It actually diverges. But I want us to investigate it, okay? Because I'm trying to get you to understand what it means to show convergence of a series. So look back at the definition I put up there a second ago. For it to converge, here's what we needed. We needed the limit, right? For it to converge, we need the limit as n goes to infinity of s sub n to equal some s, right? That's what we needed. We needed this limit to be a number, okay? That's what we needed. So what is s sub n? Let's see. Let me ask you this. What's s sub 1? What does s sub 1 mean? It just means take the first guy, right? And that's it. Don't add anything to it. That's s sub 1. What's s sub 2? 1 plus 1/2. That means add up the first two, which would be 3/2. What's s sub 3? Add up all three. 1 plus 1/2 plus 1/3, which would be, what's 3/2 plus 1/3? Anyone? Bueller? 11/6? Uh-oh. 11/6? Okay. All right. I'm off camera with that grin on my face. All right. What's s sub 4? Something else. S sub 5, right? What we've created, though, does anyone see what we've created over here? A sequence. And what this is saying is for the series to converge, the sequence we create of partial sums must converge. That means these sums have to be headed to a number. Like it starts out at 1, right? Then it goes to 3/2, then it goes to 11/6, right? And it keeps going. Is that headed towards a number? It's easy to check that this is headed towards a number, right? Just let n go to infinity. We're done. But it's very difficult to determine if this is headed to a number. Understand the difference between the two? So for us to ever be able to check to see if a series converges, we have to make sure that the nth partial sums, which is a sequence, converges. Understand or not? The way we're going to do it is going to be different for every problem, but this is the general idea, okay, is that you start with a sequence, you write the series, the partial sums creates a new sequence. We want to see if that sequence converges. If it does, that's the sum of all those together. Whatever happens as n goes to infinity. Going to move on. That was just to get you to think about what this means, all right? Just look at these sums just going towards something. Are they going towards something? What if they don't go to something? What if it doesn't go to a number like this? We'll say it diverges, right? And I'm telling you this diverges, but I'm not going to show you why yet. We'll get to that today, later, hopefully, if we have enough time. All right, so we're going to talk about now the first important infinite series. All right, there's a lot of different ones, but this is an important one. It's called the geometric series. So this is our very first series that we're going to work with, and I hope you like it. Let me turn my phone silent here. So the geometric series is any series that looks like this. You have A plus AR plus AR squared plus AR cubed plus AR to the fourth plus dot, 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 forever. That's what any geometric series must look like. Here, A is a constant. And R is a constant. So what we have in the problem, or in the series, is we have a number that never changes, right, throughout the entire sum, and then next to it a number that the power keeps going up every single time. Right? That's what a geometric series is. And the question is, does this add up to be a number, right? That's the question. Does it? And that's what I'm going to show you, all right? This is a really nice little proof, I think, right? So what is it that we're supposed to look at? In order to figure out if a series converges, what are we supposed to investigate? The S sub n, right? The S sub n. So let me write down what a geometric series would look like first in summation notation. Let's see if we can get that across. What would be another way I can write this in sigma notation? Sum. So A never changes, right? So A. You want me to do like n equals 1 to infinity? How about that? That'll create the whole list. So what's changing throughout the entire problem? Let's see. What is it? The power on R, right? The power on R, this is R to the first power. This is actually hidden here. It's really R to what? The 0 power, isn't it? There's really an R to the 0 there because R to the 0 is 1. So how can I create this list using this? What do I need to do with this R here? R to the n minus 1. Do you all see that? So every geometric series looks like this, right? Which is equivalent to that using the sigma notation. Yeah? Curious, could I have done this? Tell me if I could do this. Sum n equals 0 to infinity of AR to the n. Could I have done that? I told you never to let n be 1, right? We're always going to say n is 1? Okay, not anymore. All right? Now n can start wherever we want to start it. All right? We can. Because that was just to keep us all on the same page while we were in 8.1. But really, the rule of thumb is that n is going to start at 1, but there's nothing stopping you from starting it somewhere else. There's nothing stopping you. Look, does this create the same thing? Let n be 0. What do you get? AR to the 0. Okay. Now let n be 1. What do you get? AR to the 1. So don't you create the same series of numbers using this and this? The only difference is where I started my index, right? This right here we call the starting index. This is the stopping. I started 0 instead of 1, but I also had to adapt this part, didn't I, to make it work? So these are the most common versions of a geometric series. It's either going to start at n equals 1, and you'll have a little n minus 1 up here, or it'll start at 0, and you'll have an n up here. Both of those create that. Yes?
So in this case, n doesn't represent natural numbers?
Yeah, n is no longer going to be restricted to be It's still an integer, but it no longer has to start at 1.
But you can't, can you start at like halves or?
Has to be an integer. Can't be a fraction,
I
yes.
thought he said n is going to be all natural numbers.
Yes, that's what I'm saying, that
It's not. Okay.
not anymore. Look, when we were first defining sequences, when I wrote like, a sub n equals 1 over n, I told you that if you wanted to specify where to start, you could put out here like n equals 3. And that would tell you, okay, start at 3 instead of 1. Can you get the door, Ruben? And I told you just that the convention is that we all agree we're starting at 1. Right? We're all going to agree we start at 1. But now we're saying, look, we've grown up a little bit. We kind of understand how this works. We can start, well, could I start that one there? No, because it wouldn't be defined. But if I put plus 1, then I could. I could start anywhere I want as long as these keep going up by an integer. All right, there's going to be a lot of pills we're going to have to swallow today. So, you okay so far? It's all right? Okay, so this is our geometric series. Now, tell me what does S sub n look like? What is S sub n? Well, it would be what? This plus this until I get to where? A R plus A plus AR plus AR squared, right? We're going to use this one. That other one I showed you, just realize it's there, okay? This is the one I will use throughout the rest of the class, all right? But some books prefer to use the other one. Okay, so this is what we have, right? When do I stop? Be very careful. When do I stop? It's n partial sum, right? I'm going to stop when my index gets to n, which would mean my last one looks like this, AR to the n minus 1. Wouldn't this be the n partial sum? This would be what would happen if I started at 1, then 2, then 3, then 4, and I stopped at n. I know you're probably getting the n here confused with my stopping point. So if you want, you can look at this as like a capital N so that you can distinguish it from this little n, capital N. So it's stopping at capital N. But you need to be able to, it's the idea that's more important than the actual letter. Right? If I take the n partial sum, that means I'm going to add up using this formula and stop somewhere, right? Stop at an n. And that's where I would get to if I stopped at n. Everyone agree with that? I'm supposed to figure out now what the limit is as n goes to infinity of this, right? If that goes to a number, then I know what this adds up to be, don't I? Like if it goes to a number, if it doesn't, it diverges. What's wrong with that, though? If I ask you for the limit of this as n goes to infinity, what happens? That means there are more of these, right? That's all that means? It just means there's more and more of these. And so how do you add them up if there's more and more and more? It's impossible for us to do, right? What? No integral. So this is hard to show. So I'm going to show you how someone came up with this very clever. You ready? Here it comes. All I was trying to show you with that is the fact that we can't just take the limit and boom, we have an answer. All that the limit as n went to infinity did was added an infinite number of things to add up. It didn't actually get us to a number, right? So let's again write down what S sub n is. That's S sub n, right? And let's stop it out here at a r to the n minus 1, right? That's our nth partial sum. You'll hear that language? That's the nth partial sum. Now what I'd like to do is just multiply it times r. Look, this is not something that I would expect for you to have seen, and this is not like, oh, obviously Cal 2 students see that this is what you're supposed to do. I'm showing you something that someone else got and figured out, it works, and we're going to get a nice formula for geometric series out of it. So if I multiply this side by r, I have to do the same thing over here, don't I? So isn't this then ar squared, ar cubed, ar to the fourth, oops, I forgot the r, ar to the fourth, plus dot, 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 dot. What's my last one going to be? ar to the n, right? Because all we're doing by multiplying by r is bringing the powers on every one of these r's up, right? So the nth partial sum is this, right? The nth partial sum times r, which I just pulled out of the air, is this. Yeah? No one disagrees? Okay, now I would like for you to tell me what's S sub n minus r S sub n. So that means if you take this row, right, and you subtract this row, right? Take the top row, subtract the bottom row, what happens? Well, let's see. This A doesn't go anywhere, right? But this AR subtracting this one, that's gone, right? AR squared, gone. Gone, 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 gone. No, not everything. This one right here, isn't this one the one right before this one? Right? If this is AR to the n, then the one right before it is AR to the n minus 1. So these two will cancel, won't they? Yeah? So it's just the A that we have here, take away what? A r to the n. Yeah? Do I have a huge sum of things anymore? If I let n go to infinity, am I adding more things like I was before? Like here, if I let n go to infinity, it means move more of these out, right? I don't have a big old sum anymore, do I? A bunch of stuff canceled. Now, I was interested in this, right? This is what I'm most interested in. These both have it, don't they? So what can I do right here on the left-hand side? Factor out an S sub n. So this is algebraic now. Okay, so now what we have is S sub n is factored out on the left side. What's still there? 1 minus r. What's on the right side? A minus a r to the n. Yeah? I wanted S sub n, don't I? Let's divide through by 1 minus r. So S sub n would be equal to a minus a r to the n over 1 minus r. It's absolutely fundamental that you see that we went from S sub n meaning this plus this plus this plus this, where if I let n get big, it drew my sum out further, to an S sub n where if I change my n now, it doesn't mean add more terms, right? N is only affecting one thing here, and that's right there. Do you see that? That's all it's affecting. So let's talk about some possibilities here. If I take the limit as n goes to infinity of this thing, what could happen? What? You get big? What is r raised to a big power going to do?
Infinity.
Yes and no. Doesn't it depend on r? Like if r is 1, then what happens? If r is 1, you get 0, don't you? Right? It would be, right? Wouldn't this just be 0? But then on the bottom it would also be 0. Oh, okay. let's not let R be 1 then, huh? Let's look at some other possibilities. What if R is bigger than 1? And I'm actually going to go further. What if the absolute value of R is bigger than 1?
Then it goes.
So that's going to become infinite, right? Imagine plugging a number in here like 2. 2 to the infinity blows up, right? A is a fixed number, R is a fixed number. If I let R be bigger than 1, this thing's going off to infinity. Yes? If I let R be negative 1, or negative 2 or something like that, then this thing is still going to diverge because this thing's going to get huge and it's going to keep switching between negative and positive numbers. It's not going to go somewhere. That again is back to 8.1. So this is a problem. If the absolute value of R is bigger than 1, it's going to diverge. But what if the absolute value of R is less than 1? What do we say happens to a number when a number between 0 and 1 when you raise it to a bigger, goes to 0? If that goes to 0, then what does this become? That's 0. So all that's left is A over 1 minus R. Right? So if the absolute value of R is less than 1, then this sum, which I'm going to write S sub n, converges to, remember me using that arrow? Converges to what? A over 1 minus R. And this is the main result of a geometric series. All right, I'm going to give you examples. It's just me deriving where it all comes from, all right?
Sorry, I have a question.
Yes?
So for the top, you're only playing with the top R, you're not letting both R's be, you're defining.
I'm not letting both R's be what?
Those two R's, top and bottom, you're only playing with the top R.
No, I'm playing with both of them.
Well, if you let it be 1, then wouldn't it be 0? Yeah, which is makes sense.
If I let what be 1?
R.
I didn't say R was 1, though. I said let's not talk about R being 1 for right now. Right? This is R bigger than 1, R less than 1. Right? I'll deal with R as 1 in a second.
Not really using numbers right now, are we?
We're not what?
We're not messing around with numbers.
No, this is, well, I mean, we are. We're trying to figure out what happens to this. The only reason I'm concerned about that is because that's the only one that n is having an impact on. This is just a number, isn't it? As long as R isn't 1?
Maybe I'll just be patient.
Okay. Let me summarize this, okay? For a geometric series, so summary here. If you have a geometric series well, let's not say if, let's say given, all right? Given this geometric series, this thing can really be equal to one of two things. First of all, it can diverge, right? It can diverge. It'll diverge if the absolute value of R is greater than or equal to 1. Now, I said greater than 1, didn't I? And now I'm saying equal. I'm sneaking the equal in on you here. Why am I sneaking the equal in? Well, what if this is 1? Then what does this sum really become? What's sum n equals 1 to infinity of A? That would be A plus, now let n be 2. A plus, now let n be 3. A plus, never stop. If I take a number and just stack another, I don't care what number it is. 1/2, another 1/2, another 1/2, another 1/2. It's going to blow up, isn't it? That's going to become infinite. So it's going to diverge. So I took care of the 1 situation just by observing what would happen to this series if I let R be 1. If R is bigger than 1, then that formula I showed you a second ago, the R to the n blew up and it became divergent also. But if the absolute value of R is less than 1, then what's going to happen? It's going to converge, right? But not only is it going to converge, we know exactly what it's going to converge to. 1 over 1 minus R. A over 1 minus R. Question?
Isn't it only if it's between 0 and 1, not if it's less than 1?
It'll work for less than 1 also.
So negative 2, less than 1?
What the absolute value is.
Well, I mean, even absolute.
If you say the absolute value of a number is less than 1, that means the distance from the number to 0 is 1. So it's everything here until you get to 1, and everything this direction until you get to negative 1. So it's everything on the interior there. So it's the interval negative 1, 1, not including the endpoints. Is that okay? All right, that's it. That's the formula. Now let's see this in action, all right? Look, there's very few series that we can actually find the sum of. This is, what I'm telling you is that this is a series we can actually find its sum. Someone gives you a geometric series and the r is less than 1, absolute value of r is less than 1, we can actually figure out what it adds up to be. So let me start with an example that maybe you've seen before. Have you ever heard this thing where, like, if I were to try and walk across this classroom, let's say we measured the classroom from one edge to the next and we said that that was 1 unit, whatever it is, 1 whatever. Then if I walk halfway and stop, then I've gone 1/2, right? And then what if I walk halfway again? I'll walk this way. You're covering your mouth. I don't want to get sick. Okay, so I came from that wall and then halfway and then now halfway again. So how much have I walked now? 1/2 plus 1/2 of a half, which is 1/4. And then I go halfway again, which is 1/2 of a half of a half, which is 1/8. And I go halfway again. Right? So the picture of that is this. You're trying to go, the distance from here to here is 1. So you first go halfway. Then you go again, which is going to be 1/4. Then you go again, which is 1/8. Then you go again, which is 1/16. And you keep doing that forever. Will you ever get there? Mm-hmm. This is one of the Zeno's paradoxes, but theoretically you wouldn't get there. But we know that as you add those up, right? If you add these up, if you could add forever, it should equal 1, shouldn't it? Shouldn't it equal 1? It should. So let me see if I can somehow prove that it'll be 1 using the geometric series. So tell me what it is I'm adding up again in this picture. I'm doing 1/2 plus 1/4 plus 1/8 plus 1/16 plus, what would be the next one? 1/32. And I keep doing that forever. This is a series, isn't it? An infinite series. What I'm hoping for is that it's a geometric series, because if it's a geometric series, then I can possibly find the sum. Is it geometric? Yep. It is? Okay, what's the formula? Because if it's going to be geometric, you're going to have to figure out the pattern. I'm going to write up here. Maybe you're looking at it like this. This is 1/2 plus 1/2 squared plus what, 1/2 cubed plus 1/2 to the 4th. Right? That's what it is. Which written as a series notation with sigma would be n equals 1 to infinity of what? What are those powers up there? That's 1 on that, right? Isn't this just 1/2 to the n? It's just 1/2 to the n. Is that okay so far? You plug in 1, you get 1/2. Plug in 2, you get 1/2 squared, and keep doing that forever. Now, on the side here, I'm going to write down what everyone needed to remember. All geometric series have to look like this. This is the Big Daddy formula for geometric series, right? All geometric series have to look like this if the absolute value of r is less than 1, then I know that that thing converges to a over 1 minus r, right? If the absolute value of r is less than 1. So I need to figure out what the a is and what the r is. Can I do it yet? Yes? Does this look exactly like this right now? What's the difference? This is just n, and in that formula, it's n minus 1. So I need to make that look like n minus 1. Do you remember how we do that? Like the hidden? Oh, I could try and change that, but you have to be careful because if you change this, you have to change that also. I really want a minus 1 here? So I can do that? Right? Get used to it. Get used to it. Yes, I can do that. To try and make it look like that. All right, now, what does this become if I rewrite it? We've got 1/2 to the n minus 1. I'm going to split it right there. And then what goes next to that? Times 1/2 to the 1, right? I mean, we're just using properties of exponents here. You have the same base, two different exponents, you add them together, you add the exponents, right? So does everyone agree that this is this? Yeah? I had to do that to make it match the formula. If I don't match the formula, I can't use the formula. So it seems like no big deal that you're off by 1 there, but it's a huge deal. Your answer will be wrong if you try it any other way. So now does it look like that formula? Do you have a number by itself that doesn't have the n on it? Yes? What is it? 1/2, right? Do you have a number that's being raised to the n minus 1? Yes, 1/2. So in this particular problem, we have that the a is 1/2, and it turns out that the r is also 1/2, isn't it? So from this, I know that a is 1/2, r is 1/2. This is definitely geometric, right? Geometric series. I need to check that the absolute value of r is less than 1. Is it? Is the absolute value of r less than 1? Question. Yeah, well, absolute value 1/2 is less than 1. Check. That means it converges, doesn't it? And it converges to what? That. A over 1 minus r. So this sum right here, this sum right here converges to a over 1 minus r, which is just 1/2 over 1/2, which is 1. You need to ask questions if you have them. It converges to 1, which is what we kind of did with me walking halfway and then half of that and half of that. If I could keep doing that, theoretically, I would hit the wall eventually, right? If I could go forever doing that. That's what we're saying. This series, if you kept adding them up forever, you would get closer and closer to 1. Closer and closer and closer to 1. We may as well define it as 1 because you're going forever. I hope you can live with that. Okay? Okay, let's try another one. Find one-fourth plus 3/16 plus, you know what, let's make this one alternate. Let's make this one alternate. 1/4 minus 3/16 plus 9/64 minus 27. What am I doing here? 256 plus dot, 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 dot. So I have good news, which is that in this section on series, we've only covered geometric series. So there's really only one thing this could be right now, right? Geometric series. But let's actually figure it out. See, on a test, I'm just going to say, fine, so I'm not going to tell you what you're looking at. And you're going to have, I'm not saying this to scare you, I'm just trying to, like integrals. Remember, it's like you have all these techniques of integration, you don't know which one to use. Give you some, it could be a geometric series, could be a harmonic series, could be a telescopic series, could be all these different types of series. And so how do we deal with it? All right. Let's see if we can find the pattern, if there is a pattern. Anybody see a pattern? Okay. The denominators are all powers of 4. This is, it looks like, and the numerators are all powers of 3, aren't they? So this is like 3 to the 0 over 4 to the 1 minus, this next one is 3 to the 1 over 4 squared. The next one's plus. I don't know why I'm going back and forth between black and red right now. Really have no idea why I'm doing that. It's just fun with colors. All right, so what, 3 squared, 4 cubed, then minus the last one, which would be 3 cubed, and then 4 to the 4th. That's what it looks like is happening, right? So how do we create that series using, like, what sequence would generate those numbers? So what should you look at first? The alternating part first? It's alternating? And it's starting with what? Positive, then negative, then positive, then negative. How do we create a sequence that's going to alternate starting with positive 1? Okay, so I'm trying to figure out what our sequence is. It's negative 1 to the n plus 1. That work for everyone? All right, and then next to it, I have a fraction where my numerator is 3 to a power, but I want to start that out at 0, so n minus 1 up here. And then on the bottom, 4 to the just n, because I'm going to start at 1. That's the sequence that creates that series, isn't it? That's the sequence that creates the series. So all I need to do now is write down this sequence in sigma notation, and I have a shorthand representation of that, don't I? So let me write it down. Were there any questions on where that came from? Okay, so my series is equal to sum n equals 1 to infinity, and I had negative 1 to the n plus 1 times 3 to the n minus 1 over 4 to the n. Is that a geometric series? Doesn't look like it, does it? So what are the things that we look for in geometric series? You've got to have an r, right, raised to an n power. That n needs to be n minus 1. But overall, you need like a base that's a number, right? ar to the n minus 1. You need like a base number, and then you need the powers to be n's, right? Which I have a bunch of powers that are n's, right? But one of them is an n plus 1, the other one's an n minus 1, the other one is an n. Is that intimidating us or no? Of course not, because we got hidden zeros all day long, right? We can do that all day long. We can make all these n minus 1s if we just push them around enough, right? So I'm not worried about that. Are you? Okay, so let's make it happen. This is going to become sum n equals 1 to infinity. How can I rewrite that negative 1? See, negative 1 to the n. I need to know how comfortable y'all are with me doing this or not. So we've done it a lot. So am I good to go that far with it? Is that okay with you? It's basically n minus 1 plus 1 plus 1, right? I plug in a minus 1 plus 1 right in there. So it becomes n minus 1 plus 1 plus 1. And the plus 1 plus 1 at the end becomes 2. So I've got n minus 1 plus 2. And then I split it into 2, and there it is. Okay. Then the 3 we do, the 3 we don't even have to touch. Isn't that nice? Over, and notice I kind of slid the 1 up here because it really is in the numerator, isn't it? On the bottom, it's going to become 4 to the n minus 1 times 4 to the 1, or just 4, right? We're still okay or not? All right? Okay. This, and this are all raised to the same power, aren't they? If they're all raised to the same power, I can put them all together in a parenthesis and use that power on the entire thing. So how about doing this? Sum n equals 1 to infinity. It'll be the negative 1, right? And then it'll be the 3. What's negative 1 times 3? Negative 3 over 4. So how about this? Negative 3/4 to the n minus 1. In your homework for 8.1, if you've watched the video for the solutions, I would take like a sequence of numbers and I would create the formula for it, and then I suggested that you go ahead and try and work it out and simplify it. And I told you because you'll need it later, this is what I'm referring to. Getting the formula is one thing. Turning it into a geometric series requires a little bit more work. So is that okay that that's everything in red over there? Yeah? What's still out here, though? Negative 1 squared. Wait, negative 1 squared? That's just 1. Who cares, right? And on the bottom? A 4. So I could just write like 1/4 out here, couldn't I? Do you see the geometric series now? What's A? That's A. R? Negative 3/4. Does this converge or diverge? What do I have to check? The absolute value of R has got to be less than 1. And it is, right? The absolute value of R needs to be less than 1. That's the question. That's the absolute value of negative 3/4. That is less than 1. Check. It converges then. And what does it converge to? A over 1 minus R. So this is going to be equal to A 1/4 over 1 minus R, not the absolute value of R itself, negative 3/4. So we're going to subtract a negative. It's going to wind up adding. But I just want to make sure everyone sees where it comes from.
That's a final answer.
Now we have to clean that up. Yeah. I mean, that is an answer, but we can, this is just a complex fraction. We can clean it up. 1 plus 3/4. Get a common denominator on the bottom. 7/4. So 1/4 over 7/4 is 1/7. 1/7. That's it. What do y'all think? I've shown you an example where I wrote out the series, and then you had to come up with the formula, right? Well, this one was, right? Okay. So if someone just gives you the series, like in your homework, they just give you the series and then just ask you to use the geometric. So you just have to do all that n minus 1, turning it into what you need to turn it into. So the homework is not as challenging necessarily as this. Yeah?
You just have to prove it that whether it's
They actually tell you, show that this geometric series converges. But later on in the homework, they give you just a mixture of things, all right? You're not going to have enough today to do all your homework. I'm not going to be able to finish 8.1 today. But. Okay, I want to show you something else now. It's still geometric series. Please, make sure you watch my homework videos if you want to get some help when you do the homework, right? Because I work through all this. I show as much detail as I can. Check this out. If we are all familiar with the idea of the real numbers, right? The real numbers are peanut-shaped. Yes. The real numbers, right? Which is the number line going in both directions forever, yes? And mixed in this are all the numbers that you can think of, right? Like, except I is not in there, right? Imaginary numbers aren't in there. So when you look at all the different kinds of groups of numbers there are, there's like the natural numbers, right? Which were like, what, like 1, 2, 3. And then you got into the integers, double struct z, which is like, now you can have negatives and 0, right? And then you can start getting the fractions in there, which we use a double struct q for, which represents all the fractions. I'm just going to put fractions in here. Okay? So every number that's in here comes from this group or what? I guess what I'm asking you is there a number in here that's not a fraction? Irrational numbers, like pi, square root of 2. So really, if you look at the real numbers, there's really like two major groups of numbers. There's what we call the rational, which is basically your fractions. And another major group, which are your irrationals, which is everything that's not a fraction. And there's actually a lot more of these than these. It's hard to explain, but there's more of these guys than there are fractions in there. A lot of people believe that if I just pick a number out of here, that it's got to be a fraction, that there's always a way to write a number as a fraction, but it turns out that's not the case. Not every number can be written as a fraction, yes?
So you could use the space analogy, that help me.
Yes, I could use that. You want me to use that? I don't want to get too deep into it because I just want to get to my point, which is to try and figure out with the fraction. Yeah, let me get to this. If you want to talk more about that, you can come to my office and I'll talk about that. Okay, so look. Fractions. If I take a fraction, pick anything I want. I'm going to start pretty simple. I should be able to represent that as a decimal. And in this case, it would be just what? 0.75. And this is what we call a terminating decimal. It stops, right? It stops. There's actually zeros, right? But it stops. And I could take another fraction that doesn't stop. What would be a fraction that wouldn't stop? 1/3? It's an example of one that keeps going, but what? It has a pattern to it, right? There's a pattern to the continuation. All fractions, no matter what fraction you ever pick, no matter what fraction you ever grab, it's got to do one of these two things. It's either going to terminate or it's going to go forever, but if it goes forever, it's got to have a pattern. All right? All fractions have to fall into one of these two categories. Irrational numbers like pi, what makes them irrational is that they never stop as a decimal. They never stop. So I'll say pi is equal to 3.141, and it keeps going, right? But the thing is, it doesn't have a pattern to it. There is no pattern. Y'all with me or not? I know you're like, what the hell does this have to do with geometric series, right? So if somebody gives me a fraction, I go to my calculator or I use old school long division, I can get this, right? What if someone gives me this? Can I get back to a fraction? And not that little key on the calculator that looks like this. Fraction, how does it go? No, it goes, how does it go? DF or something like that. It's like decimal to fraction. You type it and it spits out the fraction. Some calculators do that. I'm telling you that if the fraction stops or if the fraction continues with the pattern forever, we can always get back the fraction from it. Let me show you how. First, let's take the easiest case, which is this one. What if the fraction stops? Well, wasn't that pretty easy? I mean, look, this is the tenths place and the hundredths place, right? Yes? So this just means 75 100ths. And if you reduce that fraction, you get what? 3/4. Boom. So if anybody gives me a finite decimal, I can pop out the fraction almost immediately. Yes? Yeah? Okay, how about 1/3? So what if somebody gives me 0.333 forever? And let's just act like we don't know it's 1/3, okay? How could I get that to 1/3? You ready? Here it comes. You ready? 0.3 plus 0.03 plus 0.003 plus 0.0003. Do you agree with this? That's what that is? What's 0.3 written as a fraction? 3/10. What's 0.03? 3/100. What's 0.003? 3/1000. 3/10,000. Yes? Continue. Do you see the pattern here? Do you see this is 3 over 10 to the first, 3 over 10 squared, 3 over 10 cubed, 3 over 10. Wait, did I lose this? I think I put too many. That's what it was. I went too many zeros there. 10 to the fourth. Do you agree with that? Do you see the geometric series coming to life here? I can rewrite this as a sum, n equals 1 to infinity. What number never changes here? The 3. So that'll be kind of like my a, I think, maybe. We'll see. It might have to be tweaked a little bit. 3 is never changing. And then I don't have 10 to the n. What do I have? 1/10 to the n. That's critical that you see that, right? Each one of these could have been rewritten as 3 times 1 over 10 to the first plus 3 times 1 over 10 squared plus 3 times 1 over 10 cubed. Understand? And then if I take this or this or this and I raise them, right? When you raise 1 to that power, it's always 1. So that works, doesn't it? Does that look like geometric yet? Yes and no, right? I mean, it has the right form, but it doesn't have the right power yet, right? Need n minus 1? We can make that happen. So we do this. N equals 1 to infinity, 3 times 1/10 to the n minus 1 times 1/10. And if you want to put this 1/10 in front of that, it doesn't matter. I only do that so you can see that when you put those back together, you get back this. Put a 1 on there. So what's actually the a here? It's 3/10, isn't it? So this is actually sum n equals 1 to infinity, 3/10, 1/10 to the n minus 1. That's geometric, right? That's geometric. A is what? A is 3/10. R? 1/10. I don't need to check that, right? The absolute value of that's less than 1? That's going to converge? What's it going to converge to? That's going to converge to A over 1 minus 1/10, which is 3/10. I bet you it turns out to be 1/3. 9/10, right? And when you flip it, it becomes 3/10 times 10/9, 1/3. Okay. All right, now that's not very impressive. We all knew 0.333 forever was 1/3, right? Yes? Your homework's going to be something more like this. What would 0.2424 be?
Just put out a fraction
Give me the fraction that gives you that decimal.
to the calculator.
Using calculus.
I mean, technically, the calculator is using calculus, so. or inadvertently.
Yes, it is.
Are you gonna give such questions on the test?
Yes,
So we can double check with our calculator?
absolutely, you can double check. But you can't just write the fraction down. I mean, you have to have the work. So how would you redo this? Like the other one we did 0.3 plus 0.03 plus 0.003. This is a little different though. 0.24 plus, and be careful on this one, 0.0024 plus 0.000024, and then continuing.
Because the 2 and 4 repeating, it's your 2 decimal places.
That's right. The bar goes over both 2, 4. I didn't have to write, I could have just written this. But just to show you the pattern is the 2, 4, I wrote like that. Okay? This is really, what, 24 over 100? Y'all pay attention, this problem gets really tricky, all right? 24 over tenths, hundredths, thousandths, 10 thousandths, plus 24 over tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths. 6 zeros. That's all I really need to know, right? Let's write those as powers of 10. I think it'll be a little easier if we write those as powers of 10, don't you? Which is, let's see, 24 over 10 what? Squared plus 24 over 10 fourth plus 24 over 10 sixth plus, keep going. So look at our powers. Instead of like the last problem where it was 10 to the first, 10 squared, 10 cubed, it's 10 to even powers, right? To even powers. And how do we create even? Sum, n equals 1 to infinity. What's never changing? 24. So I'm going to put that out here. Maybe that's too much. I won't go that far. 10 to what power? 2n. 2n. That's how we create evens, right? Which now, can I do this? Did anybody have a question on how I did that?
8.1?
Pardon?
That's 8.1?
What is?
Sequences.
What, how do you go from here to here? Yeah, that's kind of an 8.1. How do you create the even? That's what you're saying. Yeah, how do you create an even sequence? Well, that's going to be with 8.1 stuff. All right, can I write this 24 times 1 over 10 to the 2n? Could I do that? Is this geometric? No, why not? It's supposed to be what up there is a power? n minus 1? Uh-oh. Yeah, we can't do minus 1 plus 1 here, because even if we do that, won't it be 2n minus 1? And I need it to be exactly n minus 1. So watch. That's why I said pay attention, because this one's kind of tricky. that the same thing? Properties of exponents say that if you have something to a power, you multiply these, right? 2 times n is 2n, so I'm undoing that back to this. So that's actually not, the 1/10, which you thought might be your r, is not going to be your r. It's actually going to be what? 1/100th, right? 1/10 times 1/10 is 1/100th. So we're peeling that 2 off to create the n we need up there. Understand? Yeah, now we can do the minus 1 plus 1. But I'm going to do one more line. You see n equals 1 to infinity. We've got 24. We've got 1 over 100 to the n, changing that red thing into 1 over 100, and then the minus 1 plus 1. Sum n equals 1 to infinity, 24, 1 over 100 to the n minus 1 times 1 over 100. We're almost there, right? 24 over 100 is 24 over 100. I won't even reduce it. Sum n equals 1 to infinity. 24 over 100, 1 over 100 to the n minus 1. That is geometric. We're in business, right? You've got a here. You've got r here. Absolute value of r is less than 1. You're ready to go. So this will become, according to the formula, a over 1 minus r. The bottom. I'm going to still leave this at 24 over 100. 24 over 100 over, what's 1 minus 1/100th? 99 100ths. I tell you about my trip to the coast? I was kidding around with my family. I was like, do y'all want to do like 99 bottles of beer on the wall, right? They're like, no. And so I said, just out of curiosity, how many bottles of beer would we need on the wall if we wanted to like end our trip with end like right about the same time we end the song, we get to where we're going? You know what I'm saying? Like instead of just doing it over and over, like how many bottles would we need? I think I came up with it was like 2,476 bottles is what we needed to start with or something. So I timed it like 99 bottles of beer. I timed it and then I figured out like how long we had to go and what our average speed would be, and then divide it in, and it was like 2,000 something. Why am I talking about this?
So is that your idea of a car activity? You don't play like
I don't know, man. I don't even know what made me think of that, to tell you the truth right now. I guess whenever I get to these problems where it's all just arithmetic at this point, like my brain just starts to go in different places. Like this is just arithmetic, right? Flipping, canceling. 24 over 99. Type it into your calculator. Don't you get 0.24242424? And so something actually pretty ridiculous is happening. Notice that when we had 0.3 repeated, right, what was our answer? Our answer was 1/3. But, watch, if I take 3, right, and divide it by 9, don't I get the same thing? 1/3? Okay, so take 0.244, and then take that 24, and instead of putting it over 9, put it over 99. And you get that's this, and it's 0.242424. So if you want to do 0.371, 3 of them forever, type into your calculator 371 over 999, and you would get the same thing. You would get that. Now, look, this is just to show you there's a format, a pattern to it, right? So the most challenging problem, and one that you would see more like on a test, is like this. And it's in your homework, and I'll let you do it on your own. But when you do something like that, you can't do something quick and easy like this to get the answer. All right? So notice a couple of things about this one. The 2 is first, right? The 2's not in the pattern. Point, and there's a 0 first, and then 1, 4, 1, 4, 1, 4. So the way we break this up, 2 plus 0.014 plus 0.00014. Is that going to be right? See this? Yes? And then I'm going to let you do it. I do it in the homework video, and you can watch me do it. But this is more involved. Okay, there's a lot more involved here. So please, if you get stuck, let me know. Watch the video. The last thing that I'll mention here is a classic problem of what is 0.999 forever equal to. Rewrite that as a fraction. If you follow what I just said, like for 0.244 forever, I said, what did you have to do? Rewrite it as 24 over 99? It would just be 1, wouldn't it? Do you think that 0.99 repeating forever is 1? Is it the number right next to 1?
Like uncomfortably close to 1.
Uncomfortably close to 1?
Like coming into the urinal, going next to you when there's a bunch of other. That's how close he is.
That's how uncomfortable it is. Okay. What do y'all think about that? Look, if I have the number 1 here, and you're saying that 0.999 forever is the number right next to it, right? Can't I always find a number between any two numbers? Look, if you give me 2 numbers on a number line, I'm just going to pick them, 5 and 8. I can always pick a number. I can always find a number between them, guaranteed. Here's how I do it. I add the 2 numbers together and I divide by 2. That gives me their average. So what's this added together? 13 over 2, which is 6.5? 6.5 is the number right in the middle. So if you say that 0.99999 forever and 1 are 2 different numbers, then I'm going to be able to find one right in between it by taking the 2, adding the 2, dividing by 2. And so that cannot possibly be the number closest to 1. It actually is the number 1. That is the number 1. You've just never seen it written that way. I know it doesn't make sense, but it is. Okay? It is. There is no number that you can find between this and 1. There is no number there. All right? Now we can do this several ways to prove it. You could write it out as a geometric series, 0.9 plus 0.909 plus 0.009, and do everything we just did. And when you do all that, you're going to get a over 1 minus r, and it's going to turn out to be 1. Or I can try something that doesn't require as much work. Maybe I can convince you, maybe I can't. Maybe I won't. Let's call that x. Everyone ready? This is just for fun. All right? If that's x, everyone tell me what 10x is. What do you do when you multiply a decimal times 10? Move the decimal point over. So what is this? 9.999? Forever? Still? Okay, let me ask you this. Purely algebraically speaking, what's 10x take away x? 9? 9x? Do you agree? Okay, but what's 10x here? 9.999. Repeat it forever. Take away what's x up here? 0.999 forever. And what's this minus this? 9. So you're telling me that if x is this, then 10x is this. And 10x minus x is 9x. But that it has to be equal to this, right? This is 10x minus x. So you're telling me that 9x has to equal 9, right? Which means x has to be 1. Which means that this had to be 1 to start with. Okay, anyway.
Did you just solve the debt, the US debt problem?
That's it right there. That math is math I can't do. All right. So you're either going to believe that or you're not.
You can't pay for anything like that.
No, you're right.
You can't walk up to the clerk and be like, here's
Do you agree that that's the number 0? I mean, right? No? That's the number 0. That's pretty much what we are doing, but on the other end of it. This is the number that would be as close to 0 as you possibly could get. Because see, if I go way out here, I put a 1, then that's really close to 0, but it's not, right? But if I keep going with zeros, then it's just 0, right? Well, the 0.99 is getting you closer and closer to 1, but if you keep going forever, it is 1. It's a weird concept. Okay, one more series, so at least we can talk about it, be done with it, and then we'll pick up next class. We'll still have some way to go here in 8.2. Harmonic series. Harmonic series are not that bad. Okay, I think you'll like them. Because all harmonic series diverge, always. You just have to recognize that you have a harmonic series. That's all you have to do. So all harmonic series look like this. Sum n equals 1 to infinity of 1 over n. In fact, we can generalize this. This can become more general. The more general form of this, and the one that I'll use a lot in this class, is anytime you have a sum, really doesn't matter where we start here, but if you have a constant on top, and on the bottom you have a linear expression in the variable n, which is what we have here, isn't it? We have a constant on top. N by itself is n to the first power. That's linear, isn't it? It's not n squared. Okay. So if we ever see a constant, a number on top of a linear expression in n, we have got a harmonic series. And all harmonic series diverge. Would you like to see why? I mean, because we have to explain that's why we're here. All right, so why do these diverge? Let's write out this series right here. This is the series 1 plus a half plus a third. I think I started the class with this, didn't I? Okay, so why does this thing diverge? Let's see. What I'm going to do is I'm going to write out a bunch of these, all right? Let me write out a bunch of these. So I'm going to erase this to give myself a little more room. That series is 1 plus a half plus a third plus a fourth plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9. I don't know. I think, how far do I want to go? I'm going to go to the 16th. 1/10, 1/11, 12th, 13th, 14th, 15th, 16th. For homework, I'd like you to go out to 1,000,000. Just write that down. All right.
That'd be a bonus.
That'll be a bonus. I'll see you next semester when you're done.
How much?
All right, so this is the harmonic series, right? Yeah? I'm about to show you that this harmonic series is greater than infinity or equal to infinity. All right? So that's going to force, I'm going to show you that this sum right here adds up to be something that's greater than infinity. So what I'm going to do is I'm going to take these two numbers right here. So ignore the 1, ignore the 1/2. I mean, they're there, but don't worry about looking at them. Put those two numbers together, add those two fractions together. What's 1/3 plus 1/4? 7/12. Now we might need someone with a calculator for the next one. Don't take the next 2 and add them together. I want you to take the next 4 and add them together. Anyone have a calculator that can do that quickly? And I'm looking for it as a fraction. Or a decimal, it doesn't matter.
533 over h40.
533 over 840. All right, can you give me that as a decimal?
0.634.
0.634, something like that?
And then there is like a big number, and then there's that dash on top of it.
Okay, no, this is fine. This is what I was hoping for, something like that. 7/12, go ahead and give me that as a decimal too.
0.583,
0.583.
and then there's a dash on top of it.
Okay, so that's okay. We'll just take those. Now, I ignored the first, I ignored the 1/2. I did the first 2, added them together. Then I took the next 4, added them together. Guess what I'm going to take next? The next 8 and add them together. And when I do this, well, you know what? Maybe we don't need to add it up. Check this out for a second. Would you agree this is the smallest number in this list? Okay? This is the smallest number in this list. So this is bigger than 1/16. This is bigger than 1/16. This is bigger than 1/16. All of these? How many of these are there? 1, 2, 3, 4, 5, 6, 7, 8. So isn't this right here bigger than 8/16? Right? 1/16, 1/16, all, if there were 8 1/16, this would be 8/16. But this is bigger than that. I could have used the same logic here. What's the smallest number in this list? 1/8. How many of them are there? 4. So this is definitely bigger than how many eighths? 4/8. And then this right here, same logic. 1/4 is the smallest number. How many of them are in the list? 2. So this is definitely bigger than 2/4. What do all these have in common? They're all 1/2, right? So if I continue in my list and I go out and I take my next how many? Not 8, but take the next 16, I can be sure that they're all great, that those added up should be greater than what? What do you think? 16/32. And then if I take the next 32, I should be able to say they're all greater than 32/64. And I could do that indefinitely forever. So what I'm saying is that this sum right here is bigger than, right? All that is bigger than having a 1 plus a 1/2 plus a 1/2 plus a 1/2 plus a 1/2 plus a 1/2. Just a bunch of 1/2s together, right? Are y'all following? No, I felt like I lost you there. This is bigger than a 1/2, right? So the things I'm trying to match up, these are the same. These are the same. This right here is bigger than that, right? That's why I'm saying this sum is bigger than this. The next group of 4 is bigger than another 1/2. And the next group of 8 is bigger than the next 1/2. And the next one and the next one. But this is just 1/2s forever. And what's a 1/2 on top of a 1/2 on top of a 1/2 on top of a 1/2? Added up. Infinite. This is basically infinity, right? This one right here is going to infinity. So our sum has to be bigger than infinity, so it must be infinity itself. All harmonic series diverge. That's the best kind of proof I can show, all right? I hope you buy that. Okay? So I'll give you an example of something you would see on an assignment, right? Like so, does this converge or diverge? Converge or diverge? But now I'm talking about a series, not a sequence. Sum n equals 1 to infinity of 3 over, are you adding up all those numbers to infinity? Calm down, Ron. Calm down, Ron. Getting close? Halfway there? All right, is this geometric? What tells us geometric? What's usually the most important thing that we want to see with geometric? The n has got to be in the power somewhere, which it's not, right? So the only other thing now that we have is harmonic. And for harmonic, we're looking for a constant over a linear expression, which we have, right? This is a constant. This is a linear expression in n. This is harmonic. We're done. Harmonic, therefore diverges. Here's what a student will do on a test, is they'll tell me for some reason that this converges to 0. What did they do? They took the limit as n went to infinity, and they found out that that sequence goes to 0, which I completely agree with, but that doesn't mean that the series goes to 0, right?
How would you know if you're looking for a series or non-series?
Right here, this notation. If I say, does this converge or diverge, and I give you the series with this notation, then you know I'm looking at that, right? In contrast, if I gave you this, I would ask you converge or diverge, and I put a sub n is what, 3 over 4n plus 1? Then you just let n go to infinity there. Last thing, I've got 4 minutes, and I have enough time to show you one last thing. Is harmonic okay? Yeah. All right. So look, we have so far a geometric series which requires some work. We've got the harmonic, which requires just identification. And then things are going to start to get more complicated. So we start to have a list of tests that we're going to be using to try and help us figure out if these series converge or diverge. If it's geometric, we'll be happy. If it's harmonic, we'll be happy, but a lot of them aren't. So the first test, in the next class, I'll hand you a list of the tests. The first test that we have is what's called the nth term test. This is our first of a few tests. And here's what it says. Given what is that?
A sequence inside a series.
Yeah, just given an infinite series, right? Someone gives you an infinite series. If the limit as n goes to infinity of a sub n does not equal 0, then the series diverges. So let's translate this in the last 2.5 minutes I have. Someone gives you a series. If you look at the sequence and take its limit, if that does not go to 0, you're guaranteed divergence of the series. If it doesn't go to 0, you're guaranteed divergence. The thing you have to be very careful with on this is what happens if you look at the inside and the inside does go to 0? What does that tell you? Convergence? It actually tells you nothing. And that's where people mess this nth term test up. Think about the logic of things. If all of these guys in here, right, as you wrote these out, A1 plus A2 plus A3, if each of these guys is not getting smaller, they're all getting closer to a number. Let's say like they're all getting closer to 1/2. Then wouldn't it just be like adding up 1/2 plus 1/2 plus 1/2 forever? And that would overflow. For convergence, we have to at least have that these are going to 0. So if they aren't going to 0, it diverges. Understand? Understand? That's the first test we always want to do if we're in trouble, if we can't figure out what's going on. Take this limit, hope that it's not 0. If it's 0, you're going to have to move on to the next test. Let me show you, in the last 1 minute, 2 different series next to each other and how you could improperly use this test. So look at this one. N equals 1 to infinity, 1 to the n, versus n equals 1 to infinity of 1/10 to the n minus 1. The one on the left is what type of series? Harmonic. The one on the right? Geometric. We know what happens here, don't we? This does what? Diverges. This one converges because r is what? 1/10? So this is a convergent, this is divergent. Everyone agree? Now let's see someone screw up the nth term test. They come in here and they say nth term test. They take the limit as n goes to infinity of this one. 1 over n, and they get what? 0. And they go, shit, yeah, that means it converges. No, that's not what it means. It means that you don't know anything. Does that make sense? You don't know. It could converge, it could diverge. The only thing the n-term test is good for is if this thing came out to be 1, then you could say it diverged. You could almost call the nth-term test a test for divergence to kind of help you see that that test only tells you one thing, divergence, and that's it. Understand? We'll practice with this more. Now, what if you did this one right here? Limit n goes to infinity of 1/10 to the n minus 1. So just take that. What do we say happens if you take a number that's smaller than 1? It gets big, so it gets smaller, right? This goes to 0 too. And so you go, yeah, it converges. Well, you got lucky. It does converge, but this test didn't tell you that. You just got lucky. You see what I'm saying? Just because the inside piece goes to 0 does not mean it converges. There's an example of one that diverges. There's an example of one that converges. Yes?
Roger, why do you have n goes to 0 and not n goes to infinity?
I don't know what you're talking about. No idea what you're talking about. Have you checked into glasses? You haven't looked at glasses yet? We're done. The homework assignment for this, you can't do it all, but I can tell you at least what you can do at this point. This is off of page 443. Seven through 12, 23, and 24, 31 through 34. Those are just all of them. Now, like I said, I've done the video for all of the homework for the entire section for 8.2. It's already online, but this is not the entire assignment. We still have not covered enough of this n-term test in action, and we haven't covered what are called collapsing series. So we'll do that next time. More n-term test, collapsing series, then we move into 8.3. Have a good weekend, I guess. Catch up. Don't be behind on Tuesday, all right? You got the whole weekend. I know you got nothing else going on.